Reinforcement learning agent trained directly with hardware.
Yeah.
And so that's what is being shown here. Obviously sped up. So in total it took about 6-7 years to train this particular hardware.
How long?
6 or 7 hours in total. And so that's what we're showing here. So we do have like multiple versions of the policy. But then of course you can inject a disturbance. You can see that it's pretty robust, right? And so
Interesting. Cool.
yeah, you can try to completely knock it off. It does both swing up and balance.
Yeah.
And so yeah, that's sort of what we have here.
So this project is about finding the optimal pointing path for a large swarm of spacecraft subject to relative astrodynamics. The real problem that we're trying to solve is how do you find the shortest path to do inter-satellite communications between a single chief spacecraft and a whole swarm of deputy spacecraft, while considering that power budgeting is a problem. So this is why finding the shortest path is the most important. We model the decision-making space as a Markov decision process, and really the action space and the state spaces are you can either go into a charging mode or you can pick some ith deputy satellite from the perspective of a chief satellite. So you get a reward for pointing within a the shorter amount of time that you point, the better your reward. And at the same time also you get punished if you want to point and complete your pointing mission while you're on a constrained power budget. So we primarily looked at two ways of online planning, contrasting it with just a random policy and a greedy policy. So the random policy just randomly picks a deputy spacecraft to point to. The greedy policy picks the spacecraft that's closest to you in terms of angular distance and in terms of angular distance rates. So there's two greedy policies here. The single-step Bellman update basically does a Bellman equation update for all the possible state action pairs, and then it picks the action that would maximize your reward. And then finally we contrast it with just forward search. So forward search just picks a pointing trajectory up to a certain depth. So for example, if I have a depth of 3, I will choose satellites 2, 6, and 8, for example, and I'll evaluate that trajectory up to a certain depth. And it turns out that actually just a single step update to the Bellman equation works just as well, if not better, than doing an exhaustive forward search up to a certain depth.
Our paper is about data-driven control for chance-constrained stochastic optimal control problems. And we use a technique called kernel distribution embeddings to embed the expectation operators in the chance-constrained control problem in a reproducing kernel Hilbert space. And what this essentially does is it gives us a representation of the chance-constrained problem that is amenable to an approximation, and it also gives us a simple computation of the policy that we're seeking for the chance-constrained problem that we can solve as an LP. So a lot of this comes from the structure that's imposed by the Hilbert space. We get this linear space of functions, and because we're searching for a policy in this linear space of functions, that's what gives us this nice structure that we can use to solve this complicated problem. So we're kind of taking the dynamics and the policy and we're representing them in this high-dimensional function space, but that gives us this nice representation that's easily computable. What we've kind of applied this to is looking at problems that are traditionally very difficult. We're solving joint chance constraints and also systems that are non-Markovian, nonlinear, arbitrary disturbances, so traditionally very difficult dynamics. But this representation gives us a nice, easy way to deal with those systems, because essentially what we've done is separated the problem of the structure of the dynamics and the cost and the constraints from the problem of learning the stochasticity of the system. And that's given us this way to kind of separate the problem into a hard part and an easy part that we can solve for.
If you know about Gaussian process regression, the comparison is that in Gaussian GP regression, you're trying to fit a function, and in this, with kernel embeddings, you're trying to fit
it's all good.
you're trying to fit a full distribution, and so by embeddings, the embedding of the distribution in a Hilbert space, you end up also with this Hilbert space structure like in GP regression. And so then you can approximate things from samples. So if you were in GP regression, if you were to take an infinite number of samples, you will fit the function perfectly, right, without uncertainty. Here with an infinite number of samples, you will fit the distribution perfectly. And so if you were to have an infinite number of data, you would have exactly the distribution that characterizes the dynamics, the stochastic dynamics of your system. So then you can do stochastic control and approximate expectations.
We kind of looked at an example for a traditionally very difficult system, but what we were trying to do was essentially obstacle avoidance with a quad rotor that's carrying an uncertain payload in windy conditions. So the disturbance and the drift term on the system make it particularly difficult to control. But what we were able to compute is a policy that pulls out some of the stochastic properties that we typically would expect to see with a stochastic policy. You have this mixed probability of choosing either the safer route that goes all the way around the obstacles or the riskier route defined by the chance constraints that goes between the obstacles. So as we change this delta term to allow for more risk or to restrict the amount of risk that's allowed, you see this shifting policy where it either chooses to go around with a higher probability or to go through the risky corridor between the obstacles with a higher probability. And this is pulled out just by the LP formulation that we're looking at. Right. So when we have this low delta, this low tolerable probability of failure, most of them choose to go around to avoid the obstacles. But when we allow for a higher tolerable probability of failure, they tend to go through the corridor, which is riskier.
So it's interesting that the algorithm actually gives two mixed strategies, even in the non-convex setting.
Yeah.
Can I think of this like a like the kernel trick is happening here? So these things are all the dimension of your data set. Like that's kind of like the computational complexities.
Correct. So that's one of the limitations I would say with this technique is that it does scale with the amount of data that you have. One thing that we're looking at currently is how to incorporate prior knowledge of the dynamics into this approximation. Right now it's purely data-driven. But if you can incorporate knowledge of the dynamics, then you can reduce the sample complexity that you need in order to represent those dynamics. So that's something that we're currently looking at just to improve the sample efficiency of these types of techniques.
Yeah.
We're concerned about task specification. So traditionally, to tell a robot to do a certain task, you need to sit down to design a reward function or actually go design the constraints. What we're proposing is that, we propose. The community has proposed the image-based policy where basically you show an image to a robot, say this is the goal, and I just ask the robot to reach that goal. And traditional image-based Go conditional learning community, the methods are that you need to learn with the exact same object in the image. So to open this particular microwave, you need to see it open once before you know how to open it. What we are proposing is that what about we can go to internet and just download images of open microwaves, or even you just have a figure of an open microwave, and then feed that to the robot and ask it to do the same to do the same thing.
I joined a project that showed empirically if you learn contact dynamics implicitly, it outperforms explicit approaches. And here we're trying to understand mathematically why that's the case. So the approach that we took was we looked at how we could prove generalization error bounds for both implicit and explicit approaches. And we even discovered that what really matters too is if you move to an implicit approach, your loss function still matters. So if your loss function is essentially the same as an explicit loss, you don't gain any benefit from having an implicit representation. So if you use an implicit loss with which has two terms, so instead of strictly imposing constraints on whatever implicit variable you're optimizing over, if you instead allow for some violation and you balance the violation loss with the prediction loss, then that's why we're seeing some of our greater performance, and we can prove that it generalizes better. So really what I mean is, if you start with the formulation here, where you have some function and it can be represented implicitly like this, this is general. The only assumptions we make on these G and H functions are that they're Lipschitz. But like some examples of what fits cleanly into this formulation is like contact dynamics. So Mujoko, Drake, Bullet, they all solve this kind of problem under the hood to come up with the contact forces. So that's what this lambda would be, is it would represent contact forces in that case. So an explicit loss would look something like this. A naive implicit loss would look like this, where you strictly impose whatever constraints there are on your contact forces. And instead, violation loss, you balance your prediction error with how much you're violating these constraints. So this is our approach. And here, for some toy example, in our paper, we have the actual closed form solutions of what the generalization error bounds are. In this simple one-dimensional example, it's just a ball dropping and colliding with the flat ground. Our generalization error for the violation implicit is an order of magnitude lower than for both of these others, and these two are identical, even though this is technically implicit and this is explicit. So really your loss really matters to gain the full benefit of implicit.
Construct barrier functions that are robust to all sources of measurement uncertainty and give us theoretical guarantees of stability. But the problem is that when you put them in the real world, in order to account for all sources of uncertainty, the most safe thing you can do is not move. And so what we can do is we can analyze like the different places that we can put in parameters in order to tune how much uncertainty we want to be robust to balance performance to safety. So if you want to be performative, then you want to go close to objects without intersecting them, but you'll get to your goal in the most optimal path. If you want to be very safe, you'll go like way away from the obstacles, but it's going to take you longer to get to your destination. So that's kind of what we showed here. Is we have two obstacles that the robot doesn't know the behavior of, but it's using vision to estimate the behavior. It doesn't know the location of, but it's using vision to estimate where those obstacles are. And so he's explaining exactly this, which is if you do all of the theoretical bounds on what the most safe behavior would be in order to provably guarantee safety, then you're not going to move. And so that's like the first thing that we did is this circled policy, which is the robot actually like backs away from the obstacles because it's accounting for uncertainty in its measurement noise, it's accounting for uncertainty in the model uncertainty, these various places that we can account for uncertainty. And then as we start, like the risky behaviors are going to move you away, and then the optimal behaviors are going to move you through. So that's kind of like the different types of behavior we can see. And so what Ryan did is he's really the control barrier function expert. He constructed this tunable barrier function that has 4 key places where you can tune these knobs. And then we used preference-based learning to tune these knobs accordingly. So we showed the human two different types of behavior, and we asked them, which behavior do you like better? Which behavior do you think optimizes this trade-off of like robustness to uncertainty versus performance? And then we continued this until we found a behavior that tuned these knobs in a way that gave you both performance and safety.
This is a collaboration between ETHZ and MIT. The paper is called like Deep Interactive Motion Prediction and Planning, playing games with prediction models. So we normally in classical like autonomous vehicle stacks, you have this separation between prediction and planning. And what we try to do here is just do it at one step. What we do is that we grab ideas from current motion forecasting literature of use forecasting what the other vehicles are going to do in the future, and we learn this policy via imitation learning. And then we grab this policy and we play a game with them using iterative best response. It's a sampling-based MPC that is able to feed trajectories to the prediction model, and then the prediction model is gonna query, like, you are querying what the other vehicles are gonna do. And then you can do this iteratively, and at convergence, you found a solution, an interactive solution. The model is trained with a state like observation imitation learning, model-based imitation learning, where you grab observations of the states and you can just backpropagate through a differentiable model. In this case, we use a unicycle model to not differentiate between like pedestrians or like AVs, and we can just do everything at once. And we use the Waymo Open dataset to learn this policy. Yeah. For the data augmentation, we do a standard scene rotation and translation. To account for the covariate shift problem, we augment the data with this nonlinear least squares trajectory refit, in which like we deviate the vehicle, perturb the initial position by a certain like delta x and delta y, and also the heading, and then we refit the trajectory. This allows the model to learn more about the map itself and to learn more about collisions, for example. That's not explicitly in the loss function, but it will learn to not like collide into other agents. Each agent of interest is put in the ego center, and then the ego center is perturbed by a certain amount, so that the network doesn't say, okay, at 0, 0, it's my agent. So we tried many different architectures, but this like single step recurrent neural network is the one that works the best, but it's not that much like computationally efficient because you need to roll out time step by time step. That worked the best to learn interactive behaviors. For example, if we used an encoding of the history and decoding of the future, what we realized is that if you wanted to stop, like all the other vehicles in the scene were gonna also stop. So we spend a lot of time trying to tweak which components to add or take so that we get a network that is like reasonable for lane changes and other situations. Yeah. As you can see here, so we have two schemes, two MPC algorithms, iterative best response MPC and iterative leader follower MPC. The second one has privileged information about what the other agents are gonna do, because it's able to query how they're gonna react to the trajectory inside of the optimization problem, inside each iteration, so that you can encode rewards that are like, make the other agent stop to you. And it's able to predict that you are actually gonna make the agent stop. So it's a sampling-based planner that has this trajectory forecasting model, pi, inside of the optimization loop.
To ensure the problem of the shift constraint is that this is a user-given problem. but it may not ensure persistent feasibility. So, like for some states, there is no control.
The policy that comes out may not be actually usable. You've got a nice
So that means, like for some states, there may be no control exists that can satisfy this constraint.
I see. Okay.
Yeah, but if we here we want to find a control barrier function to replace this safety constraint, such that we can always find the same control. In this way, we can ensure it's persistent and feasible, and it can stay in the forward invariant set to keep it safe.
Okay.
The dynamics of neural network model is really hard to analyze under what condition it's persistent and feasible. So we have to use some numerical method. And the difficulty is we need to ensure the feasibility on the whole state space. Therefore, we first prove that we can only verify the feasibility on finite sample states, and then the feasibility can be generalized to the whole state space by Lipschitz continuity.
Okay.
And then we will optimize the parameters of a parameterized barrier function using evolutionary strategy until we find a persistent and feasible control barrier function. And in this way, we can ensure it's always safe.
So I'm presenting you our work, Safe Control with Minimal Regret. And the setup that we consider is very simple. So we consider the control of a linear dynamical systems perturbed by a disturbance WT. And our objectives are to minimize a linear quadratic control cost while satisfying safety constraints that define over the system state and input signals. We assume that the constraints are convex, and the usual pipeline that one would follow is assuming that the disturbance WT is either stochastic, like Gaussian, for example, and minimizing the worst case expected control cost. And this gives you very nice nominal performances, but it turns out that the control law that you've designed might not be robust to disturbances that are sustained, like, for example, a step function. Or alternatively, one could follow an H-infinity type of control and minimize the worst case control cost with the promise of being robustness to worst case perturbation, but at the same time, if the disturbances were not as adversarial as it was planned, then the control law, the H-infinity control law, would result to be overly conservative. So what motivated us, following recent literature, was to design a control policy that satisfied these two objectives without posing any assumption on the disturbances. And our performance criteria is dynamic regret. So what we mean by that is that we try to minimize the loss relatively to the clairvoyant optimal policy, which means this is the optimization problem we are looking at. So can we minimize the worst case difference between the cost we incur minus the cost we would have incurred if we were to play the policy that is optimal having known the disturbances.
Clairvoyant means the best policy?
Clairvoyant means an oracle, so it means a policy that has access to all the future disturbances in hindsight.
Okay.
And so our key contribution are to formulate this problem as a convex optimization problem.
Okay.
The solution to this problem was already available in the case there were no constraints on the systems, whereas by formulating this problem as an STP in particular, we can add constraints on the systems, and further, we can provide a quadratic problem that whose solution gives the clairvoyant optimal policy, and that allow us to include safety constraints not only on the policy we are designing, but also on the policy we are comparing against.
Okay.
And the motivation behind that is that it might be too ambitious to compare against something that knows the future and has no constraint to satisfy. So to have a more meaningful baseline, then we compare against something that knows the future but still has to satisfy the same constraint as we do. And the main tool that we leverage to solve this problem is a system level synthesis or a disturbance field reparameterization. So instead of looking at policies that depends finally on the past states, then we reformulate everything in terms of the maps phi x and phi u that links the disturbances to the input-output evolution, input-output signals. And then it was shown in paper 3 that to encode the system dynamics, it is sufficient to impose these linear convex constraints on these maps phi x and phi u. And another question is why would you actually consider linear policy? And the reason is that this policy is sufficient to attain minimum regret in the case there were no safety constraints on the system. And additionally, this choice allows for any efficient optimization through this system level parameterization. So which are the results that we get for the system? So of course, if the disturbances turns out to be Gaussian or adversarial, then there is no way we could outperform H2 and H-infinity because that's what they were designed for.
Right.
But if the disturbance for somewhere in between, then we can really get a benefit out of this policy. And even so, we also see that this regret policy we propose somehow fits nicely in between the H2 and H-infinity, as it has a lower average cost than the H-infinity and a lower worst case cost than the H2. And this results...
The percentage here is...
the percentage is the increase in control cost with respect to the best one, which is denoted with the green one. And
the best one is
yes, exactly.
1.
Exactly, that's exactly.
Okay.
And if the system is open loop and stable, then this percentage becomes even higher. And that's because the worst case disturbance for the system has even more impact on the system itself.
Cool. And how is this map constructed? Sorry.
So that one we leverage from previous work.
Right.
And it's an alternative way to encode these dynamics along an horizon.
Okay.
So then to solve this problem, we plug this expression here inside the cost that we have. And this can be written as the difference of quadratic function.
Right.
And this one is also positive semi-definite, this difference, because we are comparing against something that's the minimum. So by definition, it cannot be higher than the previous one we had. So our problem reduces to an SDP. And one of the current limitations of our approach is that actually the scalability of the semi-definite problem with respect to the time horizon. And that's why we're currently looking at what happens when we apply this policy in a receding horizon fashion. Like in an MPC, can we still guarantee that we have some regret, bounded gain on the regret against the clairvoyant policy?
Yeah, this work is all about the multi-agent system. Multi-agent system, the agent has a homogeneity and heterogeneity. The homogeneity is all about the understanding, about the common knowledge to understand this world, this environment. But each one is a different individual, so they must have the heterogeneity. So that's all about the personalizations. So in this cooperative multi-agent system, we motivate by this point, we design actor-critic type algorithms. And for the policy part, the policy is the strategies they use to interact with the environment. They decompose the policy parameter into 2 parts. One for the shared part and one for the personalized part. I think this is also similar to meta-learning. In meta-learning, people could train the neural network while share feature embedding layers, few layers, and they may only keep the last layer as the local parameters. That's all about they use to handle their local task. So we are similar. In our policy parameters, we also share a common part we use to understand the environment, the common knowledge, and we have the personalized part to know the local task. So we consider actor-critic type formulation with bi-level formulation. The main problem is to learn a good policy to optimize the common reward in the environment, and the sub-problem is that people need to do the value function approximations, global reward approximations, and they need to achieve convergence in this part to make the shared parameters in consensus in the end. And here's about the algorithm designs. Here we just assume the environment, the network is a time-varying graph. Your neighbors is keeping changing all the time. So at each moment, we only communicate the parameters we want to share with the neighbors. So we can perform a parameter mixing step at each time to mix those shared parameters. And these are single loop algorithms. Here is our theoretical results. I mean, the 2 equations is all about the convergence errors. That has a dependence on the t. It's a total update step. So it means the more iterations you consider, the smaller convergence error you will get. So that's a theoretical guarantee which converges to the stationary point about the objective. I mean, the gradient is 0. And also the shared parameters could achieve consensus. And the numerical results is we consider a pursuit evasion game. There are many pursuers, that's the agents we want to control, and many evaders. Only when the pursuers could collaboratively to catch evader, they will get the reward. So they need to be
cooperative. And they also could share a high-level similarity with others, since their objective is to reach the same evader and capture it.
So our work is about using adversarial regularizer to do policy learning guided by trajectory optimization. So basic idea is that we use trajectory optimization to generate a bunch of example data. So basically state to control IID pairs, right? And then we try to use a neural network to learn how to like mimic that trajectory optimization's behavior. So one problem with that is that when you use a large neural network, because large neural network tend to be non-smooth, while like in actual robotics applications, you will expect that with like similar input state, you will get some similar output control. So that's here. So when the state is like similar to each other, you would expect that a smooth policy, which gives you some control that are also fairly similar. So that's kind of an inherent problem for a large neural network, because, well, that's also just kind of, if you overtrain something, it means that you are overfitting your data, which means that outside of the same like data, you might get some unexpected results that are unreasonable, which inherently is because the neural network have too many degrees of freedom, and they are therefore like might be unsmooth. So generally what people do is try to apply, for example, regularizations or like early stopping for training, something like that. The neural network is imitating the expert trajectory generated by trajectory optimization, and the basic algorithm we're using is just a simple like behavioral cloning. So just simple supervised learning and assuming the data is IID. Of course it's not, but we're just trying to see how the adversarial regularization works. All right, so here, this is like our overall formulation. So we are actually solving a optimization problem that contains here first like n trajectory optimization problems, and just a normal behavioral cloning cost for a neural network. And this is adversarial regularizers that we use for the neural network. So first, here the policy reconstruction cost, like I mentioned, just supervised learning. Right? It's very simple. So the output of the neural network should be as close as to whatever data set that you have, right? Minimizing this cost. So in this adversarial regularizer, what we're trying to do is that here, so during training, we will apply a small perturbation onto the input state X, and we will expect that then the neural network output would still stay fairly close to the unperturbed output. So this in other machine learning literature is probably called virtual. It's a virtual adversarial training, something like that. So in the sense that it's like so this adversarial training is like comparing to the output of the network itself. So hopefully with this regularizer, then we will achieve a smoother neural network. So traditionally, how we solve this kind of problem is just a normal like min-max game. So you use alternating gradient descent, something like that. One problem with that is that the min-max game provides similar priority to both players. So the one player would be the policy, one player would be the perturbation. So that might be not ideal because actually in this case we care about the quality of the policy, but not like actually how strong the perturbation like is, right? If the adversarial perturbation is too strong, you are over regularizing this network, and that's not good. So what we did is that we formulate the two-player game as a stackable game. So in stackable game, you actually have leaders and followers, which have two different priorities. So in this case, the leader is a policy which have a stronger position in the two-player game than the follower, the perturbation. So what happens is that whenever leader updates its own strategy, the follower will have like some I guess, reaction to that update, right? So in this case, we also provide the information of how the follower will respond to leader's strategy back to the leader. So like by that mechanism, the leader will be able to like optimize its own strategy better. So specifically what happens is that we write the min-max optimization in this way. So this is still pretty similar, right? So we are generating the perturbation by applying some optimizer case steps. So for example, we run Adam or we run gradient descent by case steps to generate this delta K. So the reason that we write it in this way is that in this way we can then try to calculate a gradient which is called a Stackelberg gradient here. So this term captures like when you update the policy parameter W in the leader, like how much the perturbation will change. And then we can, so when we add this term up into the overall like gradient for the policy parameters, it turns out that this like just gives the min-max, so this gives the policy a better position in the min-max game. Overall we use this ADMM framework. So essentially we like distribute, like we will distribute this large optimization into many like small ones. So you can essentially in every iteration solve each of the trajectory individually and do the learning and then try to achieve consensus. Okay. So in the result we tried simulation for KUKA arm and 5 degree of freedom hopper, which is just one leg jumping forward.
Okay.
Right. And for KUKA arms, the experiment we did was that essentially achieve some task with 100 different initializations, and we try to plot the total execution costs.
Okay.
And here, like we first provide like a trajectory optimization baseline, so that should be the optimal like cost, right? And then we also tried like policy learning with no perturbation. So this all of the delta equals to 0. And also we tried Gaussian perturbation here. So it's not min-max, it's just random like Gaussian learning. And then we tried just normal adversarial regularization.
A quick question, what's the difference between AR and SAR?
So AR is just a normal min-max game, and SAR we model the min-max game as a Stackelberg game.
Okay.
Yeah, so essentially the actual difference is just that when you update the policy parameter W, one you directly use like this term, like this term, which is just a gradient gradient for cost with respect to the parameters. And with Stackelberg, you also add a new gradient that encodes like the leader-follower interaction. So we found indeed is that here actually the Stackelberg formulation does help a bit, like comparing to the normal adversarial regularization.
Your line.
Yeah. So the Stackelberg usually stays pretty close to the trajectory optimization baseline.
Yeah, I think.
And adversarial is
this
so
one, right?
yeah. So yeah. By the way, the difference between these three is that for these three, like during the policy rollout, we applied a different magnitude of random disturbance.
Okay.
So essentially, the step forward simulation by one step and then add some uniform random disturbance onto the joint states. So you see that with the Gaussian perturbation, once you add some more disturbance, it starts to perform pretty poorly. But with adversarial regulation, it does help with the robustness of the policy.
So in this work, we're looking at model-free and model-based control methods, really. So we think those are the two new paradigms that are emerging, and we looked at sort of how different or similar are those two methods, really. So we took two benchmarks. So for the model-based control, we took model predictive control, and for the model-free one, we took, okay, here's a neural network of some form. So we want to quantify what is the difference in the inputs or the actions policies generated by those two control methods for all states in some set. So for all states, we want to be able to robustly quantify the worst case difference between a given MPC problem and a given neural network. And so here we considered the simplest MPC problem, so linear dynamics with a quadratic cost. And then we had neural networks, and we got this implicit form here because it's a bit more compact to write. And what we did here to solve this problem here was we convexify the problem. So we use these things called quadratic constraints. So it came from the Papas and Murari paper. So they're quadratic constraints for neural networks. For example, the sort of sector-bounded sector conditions, the monotone conditions, or even the boundedness conditions. But there also exist quadratic constraints for MPC. So we exploit quadratic inequalities that these the arguments of the neural network and of the MPC satisfy, and those quadratic inequalities are convex outer approximations of a problem. So we combine the quadratic constraints for the MPC and the neural networks all together into the one LMI, which is this big nasty thing up here, really. And so by solving that LMI, we have a convex outer approximation for this problem here, which is defining the worst case difference between inputs. And what this allows us to do is to sort of say, okay, for any states in some set here, we can find the worst case disturbance. And we're looking to sort of use that A for transferring stability certificates between MPC and neural networks. So we can sort of say, okay, if the two are quite similar, then we can transfer stability certificates between the two. There's a lot of work now on speeding up the computation time of MPC by approximating them using neural networks, so we can quantify the error of that gap. And the bigger picture that we want to try and solve here is trying to open up the black box of a neural network. So trying to say, actually, what it is solving some constrained optimal control problem. So we want to try and explain why the neural network is generating its function mapping as a solution to an optimal control problem. And the hope there is it helps to explain why a neural network is doing what it's doing and how we can design it better. The example is just, it's an MPC problem. So it's just a standard, here is a linear system, here is a sort of cost function, and we can sort of the bounds hold in general. And as the number of neurons grows, the bounds become more conservative, but that's because we're using convex outer approximations. So this work is based on STPs, so it's not very scalable, and we'd like to try and solve that, and also a bit conservative because it's all robust. So
our paper is trying to handle the synthesis of a control barrier certificate for a node nonlinear polynomial system. So control barrier certificate means that we want to enforce the system fulfilling the safety property. So the safety property is whenever you start from the initial state, you will not enter the unsafe set. So this is our property, and we are trying to solve the problem with a control barrier function. The key insight is that if we can find a level function, so for all the state within the initial state, it is smaller than the value. And for all the state within the unsafe set, it is larger than the value. Then, along the trajectory of the system, so with respect to the level function, if it keeps decaying, then the trajectory starting from the initial state will not enter the unsafe set. So this is how we characterize the control barrier certificate. And this is the current existing result regarding under which condition Bx is actually a control barrier function. So this is not new when we know the model. But what we are trying to solve is that when we do not know A and B here, which means that we do not know the system dynamic, whether we can still find the control barrier function. And how we solve that is that we make use of a single trajectory collected from the system. So here is the trajectory of the state, and this is the trajectory of the input, and this is the trajectory of the derivative, which you can obtain that by some filter. Yes. And the only requirement for the single trajectory we are connecting is that we want the matrix N0T fulfill the rank condition here. So actually, as the key insight, this means that the data you connected is fulfill the condition of persistency of excitation. And yeah, if you fulfill this condition, according to fundamental lemma, it means that you can also use data you connected to characterize the underlying dynamic instead of using A and B. So that if you connect the data fulfilling this condition, you can convert the condition here into a data-driven version, and try to solve the control barrier certificate and the corresponding safety controller, all using data. Show this with a case study here, and this is a polynomial with x2 and x1 to the power of 2, and we need 5 data points, and we come up with the control barrier certificate.
We're addressing the problem of safe reinforcement learning. So reinforcement learning where we want the agent to obey some safety constraints in the state space at training and test time. And conventionally, if you were to do this in a very naive way, you would add a penalty to the reward function of your reinforcement learning agent. But what that means is your agent has to take unsafe actions, be penalized, and then learn to behave safely over time. We want to avoid that, and we accomplish that by composing a RL base policy with a model predictive control-based safety guide. And what that safety guide does is it takes in a distribution over actions proposed by the base policy and corrects it to behave safely. And it does this in a very minimally interventive way. So if your agent is far from any unsafe states, it'll just return the same distribution that the base policy gave it. But if it's really close to, say, hitting a wall, it'll steer away the agent at the last minute. And that gives us training time safety. But if you penalize the divergence between these two action distributions, incorporate that in the policy gradient reward function, you can effectively train the base policy itself to behave safely without having to take unsafe actions. And we have some theoretical results that essentially show that assuming the parameter vector for the base policy optimizes this augmented loss, minimizes it, then we get a safe base policy at test time. And we can pretty much remove the MPC-based safety guide.